Alrighty, in this second video, we are going to be talking about the second derivative and concavity here. So we are just going to add on what we did in the first video with the first derivative, but now with concavity. So let's say that we have a curve C. It's defined by these two parametric equations. And the first thing that we want to do is find the equation of the line tangent to C and determine the concavity at t is equal to 2. So once again, remember that whenever I want to find the equation of a line, that it's in terms of Cartesian coordinates. So I'm going to go ahead and figure out what my x and y coordinates are whenever I plug in t is equal to 2. So that's my x value. And then my y value. So that's 4 plus 4 plus 4. So that's 12. And then 2 squared is 4 divided by 2 is 2. 2 plus 2 is 4. So we get our coordinate to be 4, 12. Now that means that our slope, remember, we have to do dy dt and then dx dt. So dy dt is going to be equal to 2t plus 2. dx dt is going to be t, which means that dy dx is 2t plus 2 over t. And then if I were to plug in dy dx for t is equal to 2, that's going to give us 3. So that means that my tangent line is going to be y minus 12 is equal to 3, x minus 4. Okay, so that was part A, the equation of the tangent line. Part B says determine concavity. Well, to determine concavity, we need the second derivative. Now, here's what the second derivative entails. Essentially, what we're going to be doing here is taking the derivative of the derivative. So in this case, we are going to take the derivative of dy dx, and remember that this is with respect to t. So the numerator says take the derivative of the derivative with respect to t, and then we're going to divide that by dx dt. Now, we already know what dy dx is because in this case we knew that dy dx is 2t plus 2 over t. And because we already know that we have a denominator that is one term, I could probably simplify this a little bit just to make my life easier whenever I try to take the derivative of this. That's going to be 2 plus 2 over t. That's going to be important because now I'm going to take the derivative of the derivative. So now the second derivative is going to be negative 2 over t squared. That's my derivative of this right here. Notice how I didn't have to use quotient rule because I could just simplify this. So please don't use quotient. Simplify first and then take the derivative of this. And then we want dx dt. We already know what dx dt is. That's t. So if I simplify this, I get t negative 2 over t to the third. And then to determine concavity at 2, I'm going to plug in 2, and that gives us negative 1/4. Since negative 1/4 is less than 0, we know that our concavity here is going to be concave down, since it is less than 0. My second derivative is less than 0. All right, for number 6, they already gave us the Cartesian coordinates, the rectangular coordinates. But we kind of need to figure out what t is so that whenever we take the second derivative, we could plug in t since we don't know what that is. So what I'm going to do here is just plug in 2 for x and then solve for t. And then that's just going to give me 4. So t is going to be 4. All right, so then we need a couple of things. We need dy dt, dx dt, and then once we do that, that's going to combine them together, and then that's going to give us dy dx. So for dy dt, that's going to be 1/2 t, and then for dx dt, that's going to be 1 over 2 root t. And then for dy dx, that's going to be 1/2 t all over 1 over 2 root t. And then I'm going to plug in 4. So if I plug in 4, the top is going to be 2, and then the bottom is going to be 4. And then if I were to simplify this a little bit, that's going to give me 8. Which means that my tangent line equation is going to be y minus 3 is equal to 8x minus 2. To determine concavity, we're going to take the second derivative. And remember, with the second derivative here, we are going to cry a little bit because I probably want to simplify this first before taking the derivative of this. Because right now, I do not want to use quotient rule with all of this mess right here. So instead, I'm going to do 1/2 t times 2 root t, and that's going to give me, let's see, t to the 3/2. So notice how here, simplifying that was better than trying to use quotient rule. So always try to simplify your derivative if you can. Now, obviously there might be some cases where you can't, and if you can't, then you're just gonna have to use quotient rule or pray that it is a calculator active problem. So we know that dy dx is t to the 3/2, which means that the derivative of that with respect to t is going to be 3/2 t to the 1/2, and then all over dx dt. So in this case, we already know what dx dt is. That's 1/2 root t. So then I'm just going to plug in, what is this, 4, and then see what happens. So plugging in 4, I'm going to get 3/2, 2, 1/4. What is that? 3, 1/4, 12. So 12, which is greater than 0. So this tells me that we are concaving up at the point 2, 3. So you probably want to write somewhere that C is concave up at 2, 3 because the second derivative is positive there. I didn't write that down for number 5, but you probably want to do the same thing. So you probably want to say that C is concave down at 4, 12 because the second derivative is less than 0 at that point. All right, last one in terms of the slope and concavity again. Oh, number 6 didn't even ask us to find the tangent line equation. It only asked us to find the slope. Oops, I'm too funny. Anyways, same thing with number 7. We're finding the slopes. So you don't have to find the equation of the tangent line. So we need dy dt, and that's going to be equal to 3 cosine of t. And then dx dt is going to be negative sine of t, which means that dy dx is going to be 3 cosine of t all over negative sine of t. Now we want to find the slope at t is equal to 0, so we want to look at this right here. So then we have 3 cosine of 0, and then negative sine of 0, which, plot twist, if you look at this, that is going to be 1 over 0. So this tells me that we are undefined. Now, what does that mean? Well, that means that whenever we plug in a 0 into this, that's going to give me 1, 0. So this means that at the point 1, 0, we have a vertical tangent line at t is equal to 0. So this is a vertical tangent line at t is equal to 0. All right. So then what we're going to do here is take the derivative of this to figure out the concavity of this. Now, if you really think about this, right, notice how whenever we do our second derivative, that dx dt is going to be the same. So we have some derivative here, so the derivative of the derivative, but then we still have negative sine of t. And if I plug in 0, I'm going to get, once again, an undefined value. So this also means that my second derivative is also undefined. So what I'm going to do here is actually graph cosine of t, 3 sine of t, so that you guys can look at what's happening at t is equal to 0 and see what that means in terms of the first derivative and what that means in terms of the second derivative. So we have cosine of t, and then we have 3 sine of t. Let's see something like negative 2 to 2. Okay, and then remember that our point was 1, 0 right here. So you can see how here we have a vertical tangent line right here. And then if I do something like this right here, kind of makes a little ellipse right here. So then at 1, or at time, or at t is equal to 0, for the coordinate 1, 0, we're neither concave up or we're neither concave down right here. So it kind of looks like that t is equal to 0 is a point of inflection here. Very cool. I know. All right. This is it in terms of the first derivative and the second derivative. But in the next video, I'm going to go over the homework problem so that you guys have it, just because it's more practice.